Hello, and welcome back to Math 100. We are now ready to study section 3.2, continuous compounding. Now, in the first section of this chapter, we learned how to calculate compound interest using things like the quarterly compounding, monthly compounding, in addition to annual compounding. And we talked about what happens if we take it to extreme, like daily and minutely and secondly. And at the end, we do have a limit, okay? And that limit is called continuous compounding, which is what section 2 of chapter 3 is all about. This is going to be a short section, and we will have one formula with a very, very important number in the formula. So let's take a look at this second section of compounding interest. All right, are you ready for it? Let's get started on section 3.2, continuous compounding. Section 3.2 is on, and the first word is important, continuous compounding. Okay, we are still talking about mathematics of finance, and we are talking about compounding interest. And in particular, there is this thing called compounding continuously. Okay, and as I said before, it is not monthly, it is not daily, but it's more frequent. And what happens if the money compounds not every month, not every day, not every hour, not every minute, but every moment in time. And there is a way to calculate it, surprisingly, and that involves a limiting process. So let's take a look at what this continuous compounding has to offer. I will mostly be writing on freehand, so using the pen. All right, so again, remember in section 3.1 and in section 3.2, we are talking about a one-time deposit. So we are not making more than one deposit, all right? And we are studying what happens to that one-time deposit as time lapse and as interest is earned. Okay, so make sure you get your calculator out. And let's review our formula. This is the general formula for the amount after T years, after that money, the interest, after the principal P is invested in the amount, in the account that has the APR of R, and K is the number of compounding periods per year. And we put the money in there for T number of years, right? Now remember, KT, that would be the number of years times the compounding, the number of compounding periods per year. So this will be the total number of compounding periods. And so, for instance, if you're talking about, monthly for 5 years, that's 5 times 12. That's 60 months, right, in 5 years. So this KT will be 60. That would be the total number of compounding periods in the whole thing, in the number of years defined by T. Okay, R over K, this is what we talked about last time in section 1. That's the rate per compounding period. So if it's 12% monthly, this number will be 0.01 because 12% monthly means 1% every month. Okay, remember that? So this is the formula that is the basis of pretty much all of the calculations in chapter 3. All right, let's do an example, a comparative example to see what happens to our principal of $10,000. How will it grow after 30 years if you have 12% annually, 12% quarterly, 12% monthly, and 12% daily, right? So here are the applications of this formula. Let's say after 30 years, how much money are you going to have? This is really A30, right? Because we are talking about in all of these cases, the amount after 30 years. So first I have 10,000 multiplied by, what's going on here? In A, it's annual. So this is 1.12, right? I can just go ahead and write 1.12 because this is an annual compounding account. So for 30 years, that's 30. And this turns out to be 299,599.22. How did you get that? Well, all right, so what you have to do is on your calculator, enter 1.12, and you raise it to the power of 30, or you use this x to the y key and then put 30. That once you do that and then you put equal sign or the enter, it'll give you this value, whatever 1.12 to the 30th power is. And then you multiply that by 10,000 to get 299,599.22. Okay, simple enough. And then the second one, part B, this time it's 12% quarterly. What's the difference? Well, the difference is what you have to do is to multiply 10,000 by 1 plus, remember it's 0.12 divided by 4. That's 0.03. Basically when you're talking about 12% quarterly, it is the same as 3% every quarter. Okay, because quarter means 1/4 of the year. So you take this and now you have 4 times 30. That is the number of compounding periods in the 30-year periods. 4 times 30, 120 quarters in the 30-year span, right? So you take this amount, that's 1 plus 0.03, raise it to the 120th power. Don't do this manually, or don't do this in your head. You can't. All right. You take 1.03, raise it to the 120th power, and then you multiply that by 10,000. You will get, what do you get? 347,109.87. Okay, which is significantly more than the annual compounding, even at the same compounding, the same interest rate. Okay, we are all talking about 12%, in all of these cases, but 12% quarterly is going to give you a significantly more amount of money than 12% annually, even after the same number of years. So you can see the tendency here that the more frequent the compounding is, the more money you will end up with. Let's see if that is correct. Next, for part C, we do 12% monthly. So in that case, after 30 years, you'll have 10,000 times 1 plus, remember it's 0.12 divided by 12, because 12% monthly means 1% every month. And then the exponent will be 12 times 30. That's 360, because there are 360 months in a 30-year period. And so this, if you do this, again, I recommend that you do this part first. Okay, so that would be a 1.01 raised to the 360th power, right? And that's going to be 359,496.41. Okay, a lot of money, all right? And then, we ready for this? Okay, so that is, yes, that is more than part B, the answer in part B. So you can see that, again, more frequent the compounding is, the more money you will end up with. Okay, and then let's do the last one. If it's growing daily, what you get is 10,000 times 1 plus, remember 0.12, but you'd have to divide it by 365 to get the rate per period. In this case, the rate per day. This is a very small number. This part is a very small number, but the exponent will be much bigger. In this time, this is going to be 365 times 30, because that's the number of days in the 30-year period. And when you calculate this, it'll be $365,765.87. So it's slightly more than part C. Okay, you see, you can see that you can do this the same thing for hourly, minutely, secondly, and so on. What happens if K continues to go to infinity? That is the question that we are to address, okay? Okay, so before I go any further, I guess maybe what I should do is just to show you an example of a scientific calculator. This one just happens to come with my Surface Pro, which is my laptop. And you can take out you can, load the scientific calculator from the set of applications that this Surface Pro comes with. And by the way, you can choose a standard calculator, like that, or a scientific or programmable calculator. I'm going to use a scientific calculator. All right, let me go over what we just did. We had $10,000, or we started with 10,000, right? And then in order to calculate the first one, when you have the 12% interest for 30 years, 12% annually, what you can do is this: you can multiply this by, remember this is multiplication, 1.12, okay, raised to, and in this case it's exponent. So this exponential, oh, that's not the case. So let's see, 1.12, and then you raise it to the power of, and in this case, what you do is to take this x to the y-th power. That is about to raise 1.12 to the 30th power, okay? And this part is telling you what I'm doing. 10,000 times 1.12 raised to the 30th power. And if I put equal sign, it'll give me the answer. The answer to part A of that question was 299,599.22, and we round off to the nearest cent. All right, so that's how we get part A. That answer for part A. Okay, let's clear that. Now the second part, it's going to be a little tricky. My recommendation is to do the last part first, the parentheses raised to the power of whatever. So for part B, just take a look at the answer for part B and your formula for part B. Part B was to calculate the amount at 12% quarterly. All right, so here's what I would do. Let's say you are finding out 12% quarterly. So it's 0.12 divided by 4, and that's going to give you the rate per period. Remember, 12% quarterly is the same as 3% every quarter, right? And then you add 1 to it, and that's going to give you 1.03. That is the value inside the parentheses. Now, look at that. We are going to raise that by what? Remember, it's 4 times 30, right? 30 years times 4 quarters, that's 120 quarters. So 120, and that is the 1.03 raised to the 120th power. And now all you have to do is to multiply that by, let's see, multiply by 10,000. Okay, and that's going to give you the answer for part B, which is $347,109.87. All right, so that is how you calculate part B. Now let's do the last two quickly. All right, you have for part C, you have a 12% interest, but it's monthly. So you divide it by 12, which is basically 1%. You add 1 to it, and that's 1.01. That is inside the parentheses, and you raise it to the power of what? You raise it to the power of, because you have 12 months and 30 years, that's a 360th power, and 360 in this case is KT, the total number of months in 30 years. And then we hit equals, and that is 1.01 raised to the 360th power. We multiply this by 10,000 to get that answer, which is $359,496.41, right? Okay, so finally, let's do parts D. That is the most difficult, maybe. I put 0.12 divided by 365. Notice here, that's what I'm showing, right? What this is showing. This is going to be a very ugly number, right? And then you add 1 to it. What is that? 1.0003287 and so on. That is the inside the parentheses, okay? Now we are going to raise it to what? raise it to, remember, raise it to what power? It's 365 times 30, right? Well, that quantity has to be calculated first. So in scientific calculators, you can use parentheses like this. 365 times 30, and I close the parentheses, and that is going to give you my exponent. That is 10,950. That is the exponent. That in turn is the number of days in a 30-year period. And then if I hit the equal sign, that is going to give me all the things I need before the last multiplication by 10,000. Okay, so you multiply this by 10,000, and that would be the answer to part D, which is $365,765.87. Okay, so that's how we got those answers, right? And I'll come back to show you more scientific calculator uses in just a second. Maybe this is a good time to stop this video clip. On the second part of this, I will do the remaining part of our notes for section 3.2.